state. So, and we're also now again in a drought warning again this year. So who knows? But it gets a little bit ridiculous here because, our governor has mismanaged the entire pandemic thing to the point of being comical. If you wanted to get vaccinated, it would help if you lived in one of the Indian Native American tribes because they weren't put under the restrictions of who could get vaccinated. So all the Native Americans got vaccinated first.
All right.
Great to see so many people dialing in. We've got 20 people so far.
21 now.
21.
All right.
So we'll start in 2 minutes. So hopefully everybody that's dialing in can hear is okay. We're just literally chit-chatting before we start. So any tech issues or anything like that, please use the chat panel.
All right.
I have also started.
And if you have questions along the way, please feel free to ask. I'm quite happy to answer everyone's questions.
Where's House Christchurch today?
Cold.
Oh, is it?
Yeah. It's going to get warmer around midday, but it's still chilly. How are you guys? Windy Wellington?
No, not at the moment. It's I think it's due to be this afternoon, a southerly, but at the moment there's not a breath of wind out there. It's quite exciting.
All right.
Okay, people, we'll start in about a minute, so bear with us.
All right. Oh, so it shows a list of everybody who was dialed in. That's cool. Oh. Okay. All right.
Thanks for dialing in. We're going to start in approximately a minute. So go grab yourself a drink before we start and sit back and relax and hope you enjoy the presentation. But we'll start in it's now 11 o'clock, but I'll give it another few seconds just before we kick off.
I hope nobody has trouble with my American accent.
I've got an English accent, so hopefully they'll mind you, I'm not talking for very long. So, okay, let's start. So, thank you so much. We've currently got 30 people online, which is awesome. So thank you for taking the time to dial in this morning. Before I pass over to James, who is the presenter today, just a quick intro from me. My name's Kirsty Muckle. I'm the engagement manager for our branches. So I work with all of the branches around the country and the one in the UK as well. So always happy to hear from people. If you have any questions or thoughts, please get in contact and I'll put my email on the chat panel shortly. I'm now going to pass over to Wes, who is on our Canterbury branch committee. He's kindly organised this presentation with James. James is based in the States, so it's great that we've been able to offer this to all of our members. So thanks again, Wes, and again, thank you, James. Just before I do pass over, though, a reminder that we are recording this today and we will make it available on our website in the near future. And any questions that you have, please use the chat panel that you can find at the top of your screen. There's just a little message box. You can use that to ask any questions. Thank you very much, and over to Wes.
Thanks, Kirsty, for organising this and sharing the intro with everyone. And appreciate the support of Sheila Karimi and Cameron Chapman of Canterbury branch. Welcome, everyone. Thanks for your presence. I'm Wes Puto, one of the Canterbury branch committee members of Entering New Zealand, and I've had the pleasure of working with the presenter, James Bonander. Jim and I have worked at BFG International Bahrain in separate divisions, And then the little time I've known Jim, he has offered a wealth of experience for composites for wind energy and railway division at BFG. And then James moved to USA, where he's been busy since then with BGL Technology International's USA division. So without further ado, I'll pass it on to James.
Well, thank you everyone for inviting me, for the invitation and being here. I'm going to try, can you see my screen now? Gervais?
Yep, we can. If you could switch to presentation mode.
Okay, all right, I'm in presentation mode. And what I want to start with is, I want to talk about the use of FRP. Let me go back to the big, well, not here, just something simple. So I'll start here. I want to talk about the use of composite structures and civil uses. And what we're talking about here is in what we've been doing with the construction of composites is creating a lot more pedestrian and bicycle paths. And 25 years ago, our partner and founder, Arnie Brutker, started building these bridges in Germany. And what we found is these have become a very, very successful product in that they're very, very durable. So the benefits of going with the composites is, one, they're 75% lighter than steel. So when you have to look at just construction and handling in the field to build, they're much lighter. They're 30% lighter than aluminum. They get very high strength. You're talking about 4 times the tensile strength of aluminum. All right. The shipping costs are quite low. Because it's lighter, we don't need quite the same crane capacities and construction equipment in order to install them. It also doesn't suffer from the problems that wood, concrete, and steel do. We don't have the corrosion. We don't have to worry about the worms invading it and the bugs infestations. We don't have to have corrosion. We don't have the problem of galvanic cells. And we also don't have to deal with the problem of toxic chemicals that are used to treat lumber. As a matter of fact, the U.S. Forest Service now requires that concrete use be reduced, and also that pressure-treated lumber is not to be used in wilderness areas because of its leachates. So when we look at this, we look at the markets that we go after. And these markets include bridges, and we look at offshore. And one of the great things about going offshore is that since it's non-corrosive, it requires very little maintenance. You're not going to have the corrosion. You're not going to have the problem of mold that wood has. It holds up beautifully over a long period of time. In the chemical industry, not being corrosive and not being reactive, they tend to be very, very effective in places where you have high pH variances and places with a lot of corrosive materials. And we also don't have the problem of forming galvanic cells. So you don't have the problem of dissimilar metals being bolted together and start rusting because these break the circuit. And that's why they work very well in places like sewage treatment plants. It also, not being conductive, it's very effective in electric rail because we don't have it carrying stray currents. So it's a very good electrical insulator, and it's also used widely in the wind energy industry because, one, it's very, very durable, it's very light. Lifting the cells up onto the top of a 140-meter tower, it's a lot easier with something light like a composite than something very heavy like steel. You also find them used now in the cooling tower industry because they don't corrode and they don't rot. And you also find them a lot in other areas where we're starting to use them as reinforcement in concrete for civil engineering and many other fields.
A general question here, James.
Sure.
The impact of composites on environment. What can you see over here?
Well, what the best part about it is the United States Forest Service gives you the best description of this. So they did a problem where they actually looked at the leachates coming out of an FRP protrusion versus a pressure-treated lumber. And we found a tremendous amount of toxic chemicals coming out of the lumber. But in order to stop it, we actually encapsulated the lumber in fiberglass to stop the leachates coming out of the lumber. So it's actually a much lower imprint on the environment than, let's say, pressure-treated lumber. and you don't have the materials coming off that you have in corrosion. And in certain alloys, it could be high levels of manganese and chromium that could be coming out, especially if you have a galvanic cell. So in that regard, it has a very small footprint on the environment. So what we come into, we make pultruded parts. And the reason with pultrusion is it's directionally very, very strong. All right. It has very good impact strength. And it also gives us the maximum use of our properties so we can bring the weight down much lower than just if we made a flat panel that's just uniform in all directions in properties. And so what we do in the process is we start off taking the fibers, we form them into a stacking pattern that forms a balanced laminate. And we talk about balance, that means that there's a line of symmetry through the part so that the part doesn't warp when it cools. From there, it's taken into a bath and saturated, and it goes on. But first we have to build the glass rack, and the glass rack is very important because what we do there is that we actually lay out the materials in order, and you'll see we usually use glass. We use glass very frequently. You can use carbon fiber. Carbon fiber is conductive, and the risk with carbon fiber is it is a cathode, and it will turn everything else around, all the metals around it, into a sacrificial anode. So this is why glass is actually more effective in a civil engineering environment. This is what we call a creel, where we use summer pulled glass, and we pull large amounts of glass fibers through. Then we use what we call continuous strand mat, which actually absorbs a lot of resin and gives us cross-machine properties so that the pultruded part has strength in both the machine and the cross-machine direction. We also will, to reinforce it, we use certain types of woven fabrics. These could be stitched together biaxial fabrics. Sometimes we use woven fabrics. The difference with a woven fabric and biaxial is that a biaxial fabric has equal properties in machine and cross-machine direction, where woven fabrics are usually about 20% weaker in the machine direction than the cross machine because the fibers go up and down around as they weave it. Once you get there, you have the feed-in system, and this is where you start to bring all these parts together into a very nice organized manner. And you'll see here, as they dispense the material, they start to line up all the fabrics together so that the material is nicely organized and it becomes a very, very clean structural material. Now, one of the things you'll notice is on the side, there's a transverse creel letting out fabric. And that's because you want to wrap the edges so that when they go through the die, they'll form a nice, sharp, strong edge that is not frayed and damaged, and the material inside is protected from damage. And that gives the impact strength because, let's face it, things get hit. So there you have it. The material's getting lined up, all the layers. You have the continuous woven mat on one side. You have a servicing veil to protect it. And then you get into the impregnation area. And this is where we add the resins. And the resins themselves is basically a wet process. You put them through and you saturate them. And you want to make sure you saturate all the way through the fiber, not just coat the fiber, because what you'll end up with is air gaps, and that will make for a weaker laminate. Now, when you talk about resins, there's different ones. You have isothalic resins, which are unsaturated. Isothalic resins are very good for marine environments, and it's very good for high UV. There's vinyl esters, which also are structurally very strong and excellent for a highly corrosive environment. Modar is a new resins that are developed in Spain, and these might be what's good for New Zealand because these are excellent for high UV, far better than a lot of other resins. There are polyurethanes, which are very, very tough, phenolic, which is extremely flame retardant, and there's epoxy, which is structurally very strong, but very weak in high UV. One of the things is that we do put aluminum trihydrate into the resin as a flame retardant. So all parts are always made to be flame retardant. Then you have what we call the die, and the die is changed based on the shape you're trying to make. And it's very important that the dies are also heated because you want to cure them in the die to the shape that you're trying to create, and you have to control that temperature. Otherwise, you'll either end up with a soft part or a burnt part. So thermal controls on that are very, very important. And this
Another
is where you
question
get
here,
into,
James.
go
Sorry.
for it.
That's from Chen. What are the generic engineering properties of glass fiber?
All right, you're going to start off with
Sorry, James, you're on mute.
James, you've just touched mute. Bear with us. James, can you carry on talking? Because I think you've just muted yourself.
I'm not sure there might be something like wireless from transport system control level around you can't, for every 40
there I am. I'm back to where I am. Okay.
Perfect.
Can you hear me now?
Yeah, thank
Yeah.
you. Might just need to repeat what you've just said.
All right. So what we talk about here is the mechanical properties are 300,000 psi, or about 2.1 gigapascals is the tensile strength of glass. You have a modulus of the glass fibers about 10 million, or about 70 gigapascals for the modulus of the fiber itself. When you make a laminate, you're probably going to end up around 21 gigapascals for the modulus for a part, and you're probably going to end up around 700 megapascals for the tensile strength.
So generally
right?
5
That's
to
in
7
compression.
times.
What?
Yes. So generally it's like 5 to 7 times that of a steel.
It's going to be much stronger, but it's not as stiff. So we are much stronger. Remember, we engineer aluminum around 25,000 psi, and we do 4 to 5 times that for aluminum. But when you look at weight divided by density, that's when you see the real big benefit, because steel is about 7.84 for specific gravity, and aluminum's 2.5, and a fiber FRP laminate is about 1.85. So when you look at it for strength for unit weight, is where you see the real big benefit. So now going on, we talk about the grippers. The grippers literally is why pultrusion has the name pultrusion. This is the part that pulls the part through. And as it's pulled out of the dies under tension, it cools, and this is where we can make the part straight. Yeah. If we didn't have that, it's a very good chance the parts wouldn't be very straight. So having the parts under tension while they cool after being reacted inside the dies is a critical part to make sure that you have a dimensionally accurate part, and you don't have a lot of twisting or sagging and other nasty things that happen to parts that are just left to their own. Then we get to the saw and we cut them off. And this is basically what's really nice about it. When you order the material, we literally just pull it through and cut it to the lengths that you need. And this material will come through the machine at anywhere from 0.5 meter per minute to 2.5 meters per minute, depending on the wall thickness of the part you're trying to make. All right, and so they can pull it through and cut it off very accurately right here in the factory to the lengths that you need, and therefore there's no waste. Once we do that, we make these parts. They're very strong. All right, we're talking tensile strengths of in excess of 700 megapascals. They're light. We're talking a specific gravity only about 1.85. All right, they're not conductive and they're non-corrosive. And this is really great if you have a problem where you're dealing with galvanic corrosion, especially, let's say, a paper mill or a sewage treatment plant, or you're doing any type of chemical process plant. This really does help prevent corrosion, and it also helps around electrical components in not conducting a straight current. And when we say maintenance free, one of the big beauties of this is you can order them to the color you need. You don't have to paint them afterwards. So we can get them made to the color you need. So if you know you're going to be building a bridge and your municipality is not going to have money for maintenance, if you pigment the pultrusions, they'll never have to paint that because the pigment is all the way through the part. And they're also very easy to install. However, I'm going to tell you, you have to be a little careful when it comes to drilling. But what we do in the applications, and this is where I talk about what we do here, and our parent company, BGL Karlstad, was happy to supply these examples. This is a sewage treatment plant outside Würzburg. And this is really great because we've been able to put the decking in around it. We put the handrails in, and we've also put the ladders and the staircases are all FRP. Those components, which are necessary for your personal safety, now will not corrode. They won't conduct a straight current, and they also will hold up very well through the winter months in Germany. It gets where they have freezing weather, and it also, nowadays, it gets surprisingly warm. And also it's exposed to a very high level of a corrosive environment. So this makes it last a very long time. This installation here is 22 years old without maintenance.
Okay.
So
James, got two questions from Chan over here, mainly related to the UV. Firstly, that you mentioned ISO and MODA are good for high UV conditions. So are there test results and in practice evidence, which he is asking for? Okay.
Yes, if you want, there are some excellent standards. There is a testing to a DIN standard and to a, I have to look it up, but if you go to the chemical companies, they have a standard test for UV exposure. And what they do is they put it in underneath a very high 260 nanometer wavelength lamp for an extended period of time. And there's tests of degradation and mechanical strengths. SAMPE, the Society for the Advancement of Materials and Process Engineering, there's been a lot of papers presented on this, especially from people who are worried about exposure in the heat of the Middle East, because the Middle East also has extremely high UV, as well as Australia and New Zealand. And this has become a much bigger issue, especially for wind energy. So yes, the people who make MODAR, they will have those test results for you, as does also Reinhold of Germany for the resins they produce. And if you look at their brochures, they'll show you exactly the test results they have done by third parties.
All right, cool. And I think the gentleman from Mass Skills, he also confirmed that they have conducted UV testing with brands. As well as there was like this argument about the colored pigments versus the gray ones. Would you be able to shed some light on that, James?
All right, here's a really sad thing here. A lot of times people think of parts fading, because of color fading, the parts breaking down. The new environmentally safe pigments do not hold up well to sunshine, especially in the reds, oranges, and yellows. To get red, orange, and yellow to hold up really well in the sun, you have to use cadmium-based pigments, which are incredibly toxic. So if you want to make something that's going to hold up very well over a long period of time, white, gray, and terracotta brown are the colors that hold up best for the long period of time, because those are iron black, titanium dioxide, and a few other neutral, non-toxic pigments. But if you really want to have a firecracker red or fire engine red part that's going to hold up over time, you're going to need very toxic cadmium.
All right, cool. And one question from Fred, that you mentioned no drilling into Frb parts. What does one do?
You have to use a special drill bit. All right, and that is, you need to use a fishtail drill bit. Don't use a standard metal or woodworking drill bit. You should always use a fishtail drill bit.
And that's because of the abrasive nature of the glass.
Well, not just that. When you drill into FRP, the drill gets extremely hot. All right, and when you normally drill, and that starts getting hot, you can actually deform the resin, and that causes a massive heat up, and you'll start getting some smoking. All right, to avoid that, a fishtail drill bit or a core drill always works better. All right, and make sure that you do it wet. Don't drill dry. All right, so just put water on it when you drill. So those are the things that happen. So slightly different drill bits are needed, but the normal woodworking and metalworking drill bits are no-no. This is a section of, okay, then here's a section of electrified railway outside of Hamburg, which we installed composites alongside of. And the reason it helps is, one, we did use gray because we didn't, no maintenance. But the other part is it doesn't conduct electricity. There are no stray currents. And the other thing that it does, it also dampens vibration. One of the problems with putting up metal fencing around the railroad tracks is they rattle a lot. And what's nice about FRP, it has a slightly higher dampening coefficient, so they tend to kill the vibration and the dampening. So they tend to be a lot quieter than metal fencing. We also make FRP ladders, and what's really great about these is if you're dropping these things down into a hole, it's a lot lighter and a lot easier to install than trying to handle a metal one. The other thing about them that's very nice is a lot of these places are usually in very corrosive environments, so we know that they'll hold up well over a long period of time. And that's what makes them very, very useful, along with the grating underneath, which is also FRP. Now, a lot of times you'll run into the problem of you have a very, very conservative local government that isn't comfortable doing an all composite bridge. We build hybrid bridges, so we'll put steel struts and beams underneath the bridge, and then use a composite deck and composite railing. And the fact is, what normally goes bad on one of these small pedestrian bridges is not the beam below, but it's the deck and the handrails. So even if you're just going to have to use steel, if you have steel beams and a composite deck and composite rails, you'll actually make those steel bridge last a lot longer because it's the deck and the handrails that usually go bad. And we make them to hold up a fairly heavy load. And in this case, here's a farm tractor crossing. In a lot of areas, we use these composite bridges in farm environments where cows cross. And the funny thing about it is wooden bridges rot very quickly. The metal bridges corrode because of all the animal excrement that gets on there, which is very, very corrosive. But the composite bridges hold up just fine, and they clean up very easily with a hose. And the other thing that's nice is in the surface, we can create a sand tread. So if you want a sand tread on the surface, we can build a sand tread onto the decking and when we bolt it in. So you can make sure it's a nice grippy surface so people don't slip and fall down. And that's also usually very helpful in a lot of places, especially with bicycles, which are making turns probably too fast. This is another example of where along an electrified railway, we put up a little simple platform for passengers. Can go up and down. It's very brightly colored, so it's easily seen. It's low maintenance. It requires very little installation time. And this one has been there for 20 years without any maintenance. So this is really an example of, it's almost like fire and forget. You put it up. If you know the city's never going to have money for maintenance and to keep up the infrastructure you put in, which is the American plague, building composite ones like this or in the FRP are very good for cities that get government federal grants for building, but then don't have the budget to maintain it. And that's the advantage of FRP, because there is no maintenance to follow up.
Oh, sorry, James. An early question over here from Sandeep, that can the fiber composites replace the steel rebars as a steel reinforcement?
Yes, then there's a company there's two companies now doing this now. Originally, the U.S. Army Corps of Engineers did experiments with it. It worked. It was quite successful. And in places like the UAE, you'll find it being used more and more in construction because they have so much saline content to their aggregate that when they were building a lot of the earlier cities buildings, the buildings were exploding on their own because the corrosion was so severe. The concrete was literally chunking out on themselves. So they had to spend a lot of money to try to get where they could wash the salt out of the aggregate. And later they found they make fiberglass rebar now, which is now being used for a lot of construction. And this helps them get around the problem of they have such a high saline content for their aggregate. So yeah, it's happening a lot. We Americans are very, very conservative, not adopted as quickly. The Europeans have been faster to adopt it. So.
And on that same bridge, question from Fred that what's the cost advantage between the Frb stairways versus a similar one in steel stairway design?
And for example, this one here, the FRP material is about 10% more expensive, but you spend half as much in labor installing. So it's actually about 20% less expensive when installed. So this entire thing was installed in half a day by 2 workers. All right. It's literally snapped together as fast, and because it's very light, you don't need a lot of big heavy machinery. And because it's not steel, we don't have to put grounding straps in. So you don't have to go put grounding and equipotential bonding and that sort of stuff. So you can avoid all that and just put this in. And because it's very light, the foundation requirements are not as extreme as they would be for the heavier steel structure. So the total installation up front is about 20% less expensive. Over the lifetime of the part, it's probably about 60% less expensive over the next 25 years because there's no maintenance to be followed up. So if you look at the whole life cycle cost, it's 1/3 the cost of steel. Now, when we do FEA, and this is where we talk about one of our projects here, where we do and the analysis. This is a 55-foot bridge we installed here in the United States. And here we have a serious problem that we call as annual flooding. And so we have to look at what happens at the attachment points when we put in these little bridges, because springtime flooding is very common. And the biggest problem that happens to these bridges is not earthquake or foot traffic, but debris in the river building up against the bridge and then creating a very high pressure against it. So even though it's a 55-foot bridge, it has to be built for a 40,000-pound lateral force on it. And that's because of the problem of debris building up on it when the river floods. And so we have to take into a series of constraints. Some of the constraints are how we drill it, how we bolt it. And this is where we get into one other thing. Because it's not as hard as steel, you really want to use a torque wrench, all right? Then this is where we get into one little big difference. In the direction of the fibers, the material is extraordinarily strong, but transverse to the fiber, that's at its weakest, and that's how the bolts go in. So we have to make sure you use a torque wrench, and make sure there's always a proper washer stack on your bolts as you put them through so you distribute the load effectively. All right. Then on top of that, we have where we take 2 C channels and we form an I-beam. And we bolt those together. And then we make sure that we do shiplap joints. We don't just let them all line up in the same place. And so what we then also look at is how we attach the handrails, because that helps create a truss structure. So we're not just building a flat beam. We actually, by using the handrails, they contribute to the strength and help form a truss. And we look at how all these parts bolt together. And this is really one of the more challenging parts about it, because you want to not have to build a separate truss and then handrails. You want to be able to integrate all these components together to be as efficient as you can. And so what we look at is a couple of things that we look at here. One, we want to look at the downward load when there's a lot of people on these. These bridges have to support 4 horses. We do have Amish people in this area of Pennsylvania where this was sent. And one of the things we get at is we want to look at how it holds up. Also, if there's a large crowd on it. Strangely enough, the worst stress these things normally have is when you have a huge group of people standing around sightseeing on it. All right. And if you look at some of the ones we do in urban environments, such as the ones we did in Hamburg, which go over the street, generally the most stress on it is when there's a parade, everybody wants to go up on it and watch the parade. And that's when you're at peak load. Now, there are two different standards that we work with that, depending where you are. There's European EN 13706 or the American AASHTO standard. And I have to say the Europeans are at least 40 years ahead of us Americans. Now, when we look at the problems of two other things. One is torsion, and we have to also look at the frequency of vibration. We don't want these things vibrating to the point that we shake people off. But we also have to look at the torsional effects based on the seismic environment that you're in. And usually we have to build to 5 times the seismic force. So in composites. Oddly enough, they don't have that with steel and concrete because people are very conservative. So we have to really build for a very high seismic event. Fortunately, this stuff does great in high seismic environments. And the reason is FRP has high dampening compared to metal or concrete. You will not ever get the amount of dampening out of steel and concrete that you can get out of FRP. And so when we come into the other problem is not every FEA program will work. We use Creo, which is very popular in the automotive industry. It also is very effective with anisotropic materials and quasi-isotropic. Quasi-isotropic means that in one plane you have uniform properties, but perpendicular to the plane you have a very, very different set of properties in a quasi-isotropic. Anisotropic is where the properties are different in every direction. Most protruded beams are highly anisotropic. And because of that, STOD, which is a very popular FEA program for civil engineers in America, crashes. And it's not very, very successful trying to run the analysis with that. But with Creo, we can do without any difficulty. As I said, we have engineering standards. There's the American standard, which is the AASHTO 2018 standard, which I would actually call somewhat obsolete. It's about 25 years to 40 years behind the Europeans. The European standard, EN 13706, is based on the DIN standards, and it's probably the most current and modern standard for building with composites there is. Here's a few case studies I want to talk about. In the top left corner, you'll see is an old rotted bridge. Literally, after only 10 years out there on the edge of the Black Forest, this thing has rotted away. It didn't hold up well because one, with a warming, they have spruce beetles digging through the lumber. You have acid rain, which has done a number on it, and the fungus has taken off out there. As a matter of fact, many of the trees around it are so soft, you can stick your index finger into to about the second joint. The other one we get into is a severe amount of rust. And people don't realize this, but acid rain that they have in Europe because of so much coal burning that has gone on has now left the steel rusting away to bits. And so what we do, we can build the entire bridge right next to it. And instead of pouring traditional concrete abutments, we use what's called earth screws. They're nothing more than giant, look like wood screws that are 3 meters long. And we have a special hydraulic machine that can drive those things in. And in less than 30 minutes, we have an abutment in place to put the bridge in. And in less than half a day, a crew can go out there and replace a bridge. And that bridge that you're looking at there has been there now for 15 years. And this is what's really great about it. And when we talk about improving bicycle infrastructure, by putting this little bridge in here, the people in that village can now bicycle to the local industrial park without ever crossing into auto traffic. And as far as getting people out of their cars to use bicycles, nobody wants to go weaving through auto traffic. But if you give them a dedicated bike path so they can commute, bicycling becomes very pleasant and very popular. And this is a huge benefit that people don't understand. a lot of our infrastructure is built around cars, but it's not safe to weave as a boy growing up in New York, weaving your bicycle through 6 lanes of traffic on Broadway is not a safe thing to do. But riding on a country path dedicated for bicycles is very safe. Nobody worries, nobody needs a helmet, and they all seem to be safe. This is one of those, one of the biggest bridges we've done. And what makes this thing so special is we had a huge amount of restrictions on the installation. The B106 out of Schwerin is a very busy highway for commerce. And we were given very little time to disrupt the road. We only had a couple of weekends where we could shut down the highway. And the most difficult part of this project was getting that center beam that you see standing there, the center there where we hang the suspension cables from. That tower is made of steel. It is probably the most problematic thing in the entire installation. So this is called a two-span cable stay bridge. It's good pedestrian. We have a 4-ton load, 3-ton per single axle load requirement. And yes, they do drive snow blowers up here to clean these. And the other place is, if you look on it, you'll find a place called Schwerin, Germany. You'll see where you can look on a Google Maps. If you can look down, and you can see it today where it crosses the B106. Our engineering office was Form Nord. They helped do it. The project manager was Brutker GFK, which was the founder of BGLTI. The structure calculations were done independently by 2 other engineering firms to confirm it, and external testing was done by Werner and Nordhaus. And so the reason for this is the Germans do not allow you to validate your own calculations, all right, which is smart, all right? So materials that we used originally came from, hello?
Hey, yeah, just another question over here from Chen. That is the range of dampening percentage for FRP structure. What is that? If there's any calculations done on that?
Yes, you actually can do it. It's done rheometrics. Normally we measure it in terms of what a term you'll see called tan delta. And generally it's 0.03. Comparison, steel is about 0.001.
Okay. And another question from Chen, that is, have any tests been carried out on FRP protruded sections related to ductility under transient cyclic loading, typically for seismic events?
Yep, absolutely. For matter of fact, University of Milan, University of Hamburg, and almost all the manufacturers, if you go to look at the data from creative protrusions, or you go look at the data from any of the major protruding companies, cyclic loading tests are very, very common and required. Usually 100,000 cycles is the standard test, and they require less than a 1% loss in mechanical properties. So actually, there's a lot of great papers published by SAMPE on the subject, but I can tell you right now, as far as cyclic loading, the Army Corps of Engineers in the United States and the German Building Institute have also done a tremendous amount of cyclic load testing, and the Germans go up to 10 million cycles when they test. So it's been quite extensive, especially by the Deutsches Building Institute. So any other questions?
That's all. Thanks.
Okay. All right. So what we did is we have the materials here came from creative protrusions in the USA. The resins are an unsaturated resin, and these are 70% glass content, 30% resin. These meet the German construction standards of the EN 23, and they are both UV and fire retardant. And they meet the UL 94VO flame retardancy. Now, what's a little different is, and now in the new flame retardancy, not just are they flame retardant, but they're also non-toxic. So you can't put out the fire using toxic chemicals. And by UV resistance, what they're looking at is the, it's a Deutsches, there's a DIN standard that it's all built to for UV resistance, basically simulating 25 years out in the sun. So what we do here, we prefabricate the entire bridge next to the site. We don't actually fabricate the bridge like they normally do. And the reason we can do this is the parts are light enough that we can now, we'll be able to move them into place. So next to the site, we'll start, do our cutting, machining, and any of the FRP modules that we need to make. And so what we do is we build up a framework and we build the regular beam structure. And if you look at it, it looks very much like a traditional steel beam structure. So it doesn't look that much different. If you look at it, the bolting assemblies, the shape of the beams, they look very much like a traditional steel construction. It's not that different, and it's not. But the difference is this is going to be 1/5 the weight of the steel, and it's also considerably stronger. Now, here's the interesting thing about it. Because this material has a little bit more flex and more dampening, it's a little bit more forgiving during the installation. So what we do is we always use naval stainless hardware. And the reason is that it's 300 series stainless is a little too ductile for our hardware. The Europeans do not use galvanized bolts. In the United States, they require that you use galvanized bolts. I personally will tell you this 400 series stainless that they use is actually far superior to the galvanized bolts. All right. So after we drill the holes, we always seal the surfaces. And the reason we, with gel coat, we then, this is where we mix up and we put the materials and we make the adhesives when we glue some of the beams together. You have to remember this bridge now is 23 years old now. So back then, this was this was the first suspension composite bridge in Germany. So we had to make sure that they wouldn't let us just bolt it. We had to glue all the beams together. All right, now we know that's overkill. Then on top of that, we have a very strict quality control, and we had to have a third-party engineering firm to do the quality inspection on site. And also, of all the materials that we had, they took samples away and they did their testing at an independent test lab. And they tested the strength of our glues, the strength of our beams, the bolts, even the concrete that was poured for the abutments. So, and they tested all the steel. Then then all the engineering work, which was carried out by the Paul group, we even installed sensors now. You can see them here. At this time being the first composite suspension bridge in Germany, what we found is that this was required to have sensors in it because they wanted to be able to detect if there was ever going to be a problem. So you'll see we actually built into the bridge a series of sensors that could tell you if the bridge is starting to fatigue or not. So we have the monitoring system put in there. It has been monitored now for 23 years, and it's not needed any maintenance. So we take the flat sheets, we glue these together, and we make these 30mm plates, and we put them in between the main beams, and this is how we make a reinforced I-beam. And these panels here, these hold up extraordinarily well. Throughout the German winters, it gets sleet, snow, it gets salt spread on them as part of the de-icing routine, and it gets all the pollution from the trucks blowing on them, and they've held up just fine. And what we have here is, this is what a cross-section of what the bridge is going to look like before the deck is put on. And this is what it is. It looks very much like a traditional metal construction, but this is the first fabrication. And so you have the standard I-beams going lengthwise, and you have your cross supports built in, along with a reinforced sidewall to make sure that the pedestrians don't fall off. And it's also designed so when the snowblower goes through, it doesn't dump material onto the oncoming traffic. All right, so this is designed to make sure that we contain whatever mess there is, stays on the bridge and doesn't go crashing down. And it doesn't drain onto the highway to create any type of visual problem for trucks getting doused and losing their visibility. So,
James, question from Nathan over here, and I think perhaps you could highlight some of the examples from Windstrip. That can these composites be used for telecom tower structures?
yes. For matter of fact, they might actually be better. And the reason is a lot of the housings on telecom structures are FRP because these are radio transparent. And what really could help quite a bit in a lot of cell phone tower applications is if you were to use more FRP, you'd actually create less interference and echoing on the radio transmission. So by using more of these FRP parts that are radio transparent, you might actually improve the quality of the transmission, all right, and help reduce the number of dead spots from the transmission from a tower. The other thing it also does is if there's a stray current, you'll protect the electrical components from any stray current head going up. The vertical support structures, okay, are made from channels. We take flash sheets and we take L sections and we glue these together, and then we bolt them together. And these are then glued and bolted to the main beams. And these become very critical as a component. You're talking about 30 millimeter thick main beams, and the secondary beams are 10 millimeter thick. All right, in the upper and lower assemblies. And this is how you form a giant I-beam. And this is how these structures are seen. You'll see that we can do this on site, and here we had to create a temporary building because the weather is so miserable and near the North Sea. So what we have is we have a special primer that we put on there, and we have a special urethane coating. And it's 160 microns thick, which is rather thick, but it is very good for weather resistance. And you have to remember, one of the problems dealing with the North Sea in this area is there's a very salty wind. They have very high winds. The weather can get very rough. So these type of coatings they thought were very necessary. Today we know that we don't really need them, but 23 years ago it was thought very, very critical that we do it this way. And then the last step in the fabrication. This is where it gets become, to me, one of the more interesting things about this. The bearing parts of the structure and the insulation of transportation, handrails, all this stuff can be done and installed on site. But what we can do here, and if you look at this bottom piece here, before it even gets moved, we can put them together into two parts. One was 19 meters long and the other is 26 meters long. And what's really great about this is there is no way you could build this out of concrete and roll it into place on the back of a truck. It just wouldn't happen. And if you did it in steel, it would be a very difficult task to try to lift that into place. All right? So that's the first part of it. So you couldn't do this in concrete and you couldn't do this in steel, but we can just roll it into place, take it down the road, and it is very easily lifted up and installed. And what's happened with us is we only had 2 weekends where we could actually interrupt the road, and we had to do it at night. So on the access road, we lifted up the 19-meter section, and we were only allowed to disrupt that roadway from Friday sunset until Sunday sunset. And so we both had to install that entire 19-meter section in 1 weekend, but we were only allowed to disrupt the road underneath for 1 day. So that structure you see down there, that went up on a Friday night and had to come down on a Saturday morning. All the rest of the installation was done with the roadway on the access road being fully usable. The second part was the 26-meter section. This had to be done at night because that went over the main highway and we weren't allowed to disrupt it. And the supporting structure we built couldn't block the main road. So we had to come in on a Friday night, starting at 10 o'clock at night. We lifted the parts in, bolted it all up. And by sunrise, the part was completely bolted together. All right. That's Arnie Brutker, our founder. And a funny thing about him, I think he's happier out there in the pouring rain doing that than putting him in an office. He absolutely hates sitting in an office. He can't do it. But he'll gladly go out in the middle of the muck and the rain and build. But I think an office for him is just horrible. And this is one of my favorite photos about this project. And this is what I really like to mention here. You can see that beautiful bridge now that goes across there that now connects a very residential area to what is also later a very large industrial area. And this allows people to commute by bicycle to and from an industrial area to the commercial area by bicycle. And it makes it now only take about 6 minutes to get there. Whereas before, you'd have to ride quite a long distance on a bicycle and have to get out into the car traffic. And this encourages people to live a more green and environmentally friendly lifestyle, because now cycling is actually faster than driving a car. On the left is what I call the bane of all projects. So after everyone who's done all their hard work to build this, what you get are 3 politicians who had absolutely nothing to do with this, cutting the ribbon and taking the photo moment, and not a single person involved is ever seen. It's the plague of being an engineer. It's our fate that, the politicians get the camera and we do all the work. So after 23 years, there has been no maintenance done on this bridge. It has not had to be painted. It hasn't had to be had any maintenance. It only took 2 weekends where we had to disrupt the traffic to put it in. And because of its lightweight, we were able to do a very fast installation. And one of the beauties here is, if your city has the money to build it but doesn't have money to maintain, it makes a lot of sense to build with materials that aren't going to need much maintenance, all right? So this is where you get to it being very advantageous.
All right, Jim, 2 questions over here. One from Johnny. That are there like composites cables being used over here as well, or were is it just like steel cables?
These are steel rods.
Okay.
The German government back then wouldn't allow it. Today, we can get carbon fiber rods, but 23 years ago, the German Building Institute didn't allow it. Now they're allowing us to start using carbon fiber rods. That only started a few years ago, but 23 years ago, we had to go with steel rods. Those aren't cables. Those are steel. Those are high tensile rods.
Okay. And the second from Kyle, that long, lightweight structures can be prone to dynamic wind loads. What wind loading analysis was undertaken and what was included in design to mitigate these effects?
All bridges that we build are subjected to what we call an extreme wind event, which is a 100. The German standard used to be 150 kilometers an hour wind for 30 minutes, and we looked at the vibration and what would of the bridge. So this bridge here, however, is not that far from the North Sea, and I can tell you it has had a 171 kilometer an hour wind event on it without incident. So this is part of the thing that we get at as far as making these structures, very, very strong. They do flex a bit more than a steel bridge does, but they hold up just fine. The strain on it is quite minimal.
All right. We got more incoming questions over here. One from Ariuna. I hope I'm pronouncing it right. So the maintenance for that after 23 to 25 years, what's that like? And the earthquake situation, how does that behave in that?
All right. First off, the only thing that's had to get maintained was the steel rods and the steel tower. They have to get repainted. The composite itself has not had any maintenance. After 23 years, They do have, the engineering firm does come out there to check the tension on the steel rods. None of them have been replaced, but they have been sandblasted and repainted, as has also the main tower in the center. So the steel sections have been undergone maintenance, but none of the composite has had any maintenance in 23 years,
Cool.
which is a huge financial savings.
Yeah, it is. Big time.
So this is actually an example of, a lot of times you want to build bridges out in a wilderness area, and it is not feasible to go and schlep the material in. And if you have a lot of wonderful nature trails that need bridges, they have to be flown in. And because we can do in composites, they're light enough that we can fly them in. What I can tell you now that I've learned, if you want to do high altitude and decent loads, a Russian Mil-26 helicopter modified by the Indian Air Force can deliver bridge sections at over 5,000 meters. I didn't know that, but only American helicopters couldn't go much over 4,000. But the Russian one can do 5,000. Neither could the French ones, but the Russian M26 that can lift a bridge segment and deliver over 5,000 meters. This is my favorite example of the Wildebeest Bridge. This has a kind of a wonderful story behind it, because environmentally, in the current day, and the Green Party being very big in Germany, and everyone talking about protecting the environment, this is a bridge built with environmental concerns in mind. And Odebrücke is an area where it crosses from the Oder River from Germany to Poland. And there are nature preserves on both sides. And there's a lot of wonderful ground nesting birds and storks in the area, which are just really critical to the environment. And also, storks are such an important part of German and Polish folklore that much of the construction had to be done in the winter months before the storks migrated back. So this bridge has it's kind of an interesting story. It's 338 meters long. Originally built in 1918, it was destroyed by the Germans to stop the advance of the Russian army in 1945. The DDR rebuilt it in 1952, and then the bridge basically fell into disrepair because it's not big enough to hold the loads of modern railways. You can't put double stack container cars onto the freight cranes going in there. You can't send the new modern German double two-tier passenger trains through. The rails themselves were made from a less than good quality steel back in the time of the DDR. So it's not the strongest steel that you could use for making rails. And what happened is we took 3 broken bridges and we recycled the framework from 3 bridges and put them onto 1 bridge where the posts or the foundations are already in the river. So we don't have to go and build new piers out in the river for the bridge. And this is really kind of a wonderful example of recycling and the 3 R's: reduce, reuse, and recycle. So we're reusing the trusses that were originally used for the trains, and we're putting them back up onto the bridge. We're reusing the existing piers in the water, but now what we're going to do is we're going to change the deck. And what we do here is we're simply now replacing the surface from being a rail bridge to being a pedestrian and cycling bridge. And this is really one of the wonderful things about this is we're now repurposing an old bridge that was once a rail bridge, and now it's being repurposed into a pedestrian and cycling bridge. And so what we have here is this bridge, you look at it, you can see the different trusses from the different bridges that it came from. But we never disrupted any of the flow of the river. No disruptions to nature preserves, all right? We used existing structures that were basically no longer fit for their original purpose. So we repurposed them and built this bridge and gave it a new deck. And the entire cost of this is less than the 10th of building a new bridge from scratch. And this is where I would really like to say that this is where you make a really fantastic improvement in infrastructure, because no matter where you go, you're going to find decaying infrastructure that isn't fit for its intended purpose, but it can be repurposed. And as we try to get people to be more clean and green, and the problem is all our infrastructure was in America was built around the car, but we want people to ride bicycles, but our infrastructure wasn't designed to accommodate them. And this is where you can repurpose infrastructure to start accommodating cyclists and pedestrians. And now, in this project that we're working in, you can now cycle from Poland to the French frontier on bicycle paths without ever crossing into auto traffic. And for those who want to go on cycling vacations and that's quite significant. But if you really want to get people to be bicycle commuters, getting them out of the car traffic and giving them dedicated bike paths makes a tremendous improvement. And in this case here, the people from Poland and day workers from Poland can cycle into Germany very, very easily now. And so you have an ample supply of where workers can cross that river by bicycle much more effectively than having to go all the way down the river and having to drive a car all the way around. And so environmentally, we've done a lot of things that are very, very good here. And I'm quite proud of this one. And it looks like there's a lot of other structures like this that we can do that with. And this also makes the area more livable and more enjoyable, because with more bike paths, people discovered that business actually picks up because cyclists also spend money. Well, I want to thank Charvet for giving me this invitation, Christy for setting the opportunity, and my partner Arnie Brutker and Nitin. Without Arnie's work, we would have nothing to talk about, and without Nitin, there wouldn't be a company to talk about, really. And if you are curious, you can contact us at bglti.com or just email me at jb@bglti.com. Thank you.
Thanks, James. That was like really insightful presentation. And thanks, Kirsty. Thanks to both of you for sparing your time. We've got one more question here, James, from Emily. That what's the installation equipment needed for the bridge that was flown to site by helicopter? That is, how were the earth screws installed in?
All right. So what you do in the case of earth screws, for that application there, what looked like is a giant Spanish windlass, about 5 guys turning the screw into the ground. All right. And they sat there pushing this thing around by hand because we couldn't drive a hydraulic system in place. Aside from that, they hiked in with we dropped off a set of wrenches and several electric drills with batteries. It took, each guy went through about 4 sets of batteries on the final installation, because really after they put the earth screws in and they bolted in the top of the abutment, all they had was a set of anchors that they had to connect. So there was very little work on their part. So they had to use some electric sockets, or you call spanners, to drive them in, and a set of torque wrenches. And that was all it took. I mean, the hardest part of all was just getting the helicopter to be stable enough to just put it down in the right place because of the crosswind. So basically it was 3 men on the ground who really did most of the bolting, but 5 guys to turn the earth screws, which was done a few weeks earlier.
All right, cool. And Ariana, I think she's requiring a bit more of a clarification about the earthquake situation. If you could highlight that again.
Well, the fact is, earthquakes vary depending on where you go. So I'm going to talk about Oregon. We have several problems here. One, we have an earthquake problem, we have a spring flood problem, and we also have a volcanic issue, and we have the spotted owl. So what we have here is, generally, we build to a maximum 5 times what we think the seismic event that is probably going to happen. So here, where I live, a 7.7 earthquake has happened, all right? So we'll design the bridge for 5 times that load when under full load. So imagine the bridge with everybody on it, and then 5 times the shock load of a 7.7 earthquake. And that's what we simulate in our FEA model.
All right. Another question over here from Harold. That are FRPs fire rated, and are there approvals or tests carried out for these?
Yes, and depending on what country you're in, there's very different ones. The Germans have a DIN standard. In America, we go by the Underwriter Laboratories 94 VO standard, which means that you subject it to a torch and it cannot carry a flame. Once you pull it away, it has to extinguish itself. So we use in the US the 94 VO standard. In Germany, there's a DIN standard for that. And for Japan, there's a Japanese standard, and India has an Indian standard that we've gone to. But they're all very similar to the UL 94 VO standard.
Yeah. Robert James, when we were doing those railway composites, they're mostly using the French standards for that, M2F3, MOF1, like that.
Yes, that's the railroad standard, and I'm going to tell you, it's almost the same for the car auto industry. It's the same for our composite bridges. It's also the same for many other components that for which human beings will be standing on or in. So basically, anything that has a human compartment will meet that same French standard.
Cool, thank you. And Sandeep is asking for, like, are there any cons for composites? Any negatives that you foresee over here?
One, they're not great. They have a very high coefficient of thermal expansion compared to steel. And at minus 67 in Antarctica, FRP has a problem, all right? It can get very brittle at below minus 40, all right? So below minus 40, composites become extraordinarily brittle. The second part thing that you get at that may be a real con against them is that if you're trying to contain a radio wave or an EMF field, FRP won't do it, all right? So that's why they use them for radomes. But if you're trying to shield something from an EMF source, it won't work. The other thing that you'd find is they don't, when lightning strikes, and this is where you get into my time in the winter industry, FRP, unlike steel, it doesn't conduct. So what happens is you have to put, if you're worried about lightning strike, you'll have to put a grounding line into it. But the fact is, they normally go up in fire when lightning hits. All right, the cable itself vaporizes, not the composite. The cable, the copper cable, literally will vaporize, and that creates a pressure pulse. So in that regard, there are some downsides. The other thing is, if you're looking for very high stiffness, fiberglass isn't what you're looking for. You might want to look at carbon fiber.
Yeah.
But some people, certain applications, it's not about strength, it's about stiffness. And so a lot of times when people are looking for extremely high rigidity, FRP is not the best choice. So if you're looking for extreme rigidity, give an example, a golf club. You can make carbon fiber ones because that has a modulus that's around 70 gigapascals, or about 10 million PSI for a laminate. But if you make a golf club shaft out of fiberglass, you're swinging a noodle. It's horrible. You've never seen. You'll be the worst golfer you've ever seen, and it has a lot of torsion to it. So, for applications like a golf club, it's not very good.
All right. Cool. All right. If there aren't any other questions, we'll wind up the presentation. And thanks again, James. Thanks for linking in from US. And everyone, have a great day.
Thank
All right.
you.
Well,
We
Thank
have
you.
recorded it today, so we will provide a recording to everybody that's registered in due course. So, but thanks again, James, for dialing in, especially from the States, and Wes, again, amazing. Thank you for organising.
No worries.
All right.
Thanks,
Thank
everybody.
All right.
Have a great
All right.
day. Bye.
See you all. Bye-bye.
you. All right. Oh, there we are. We're still recording. Okay. So that's not bad. A few minutes to spare.